non-inverting amplifier versus Schmidt trigger. Okay, where is the problem? Let me show you this. Do you all recognize this circuit? What is it? Non-inverting amplifier, right? You know the answer to what is the gain? 1 plus R2 by R1, right? You all know the derivation, but let me go over the derivation with you once quickly. So what do? We say this is the current I1. Okay, the current I1 I can write as 0 minus whatever is the voltage at this node, which is the V inverting node, divided by R1. Fine, that's the current flowing here. Then what do we say? This current is equal to this current, right? And what is the assumption that we make to say I1 equal to I2? Input impedances. All right. So I write, okay, you're saying input impedance is very high, and the current going into the op-amp is negligible, so I1 is equal to I2. All right. So you're assuming input impedance is high. I2 is equal to I1, so I2 we write as whatever is the voltage at this node minus V0 by R2. Fine. And we've already said I2 equal to I1, so we equate the two. And so we get V0 equal to V minus whatever is the voltage at this node, 1 plus R2 by R1, right? So I've made one, what you're saying is we have made one assumption, which is the current going in is small relative to the currents which are flowing here. All right. How do I write V minus? Well, we know the general op-amp. What is op-amp? Op-amp, the output voltage V0 is equal to the open loop gain of the op-amp multiplied by the net voltage at the terminals of the op-amp, which is V in here minus the voltage at the inverting. Correct? Of course, if you this is where we are heading. If we take AOL open loop gain, which is very, very large, what you will find is that the voltage here is the same as the voltage here, right? That's where we are headed here. But let's go forward. So then we can write V0 here. The voltage at the inverting terminal, one can take it out from this one, plug it here. So we get this expression. And also the voltage at this particular node that you see here, inverting node, is V in minus V0 by AOL. And then what do we say? Let's assume that the gain is very high. Open loop gain is very high. And so this part goes to infinity. Say AOL going to infinity or very high. So V0 equal to V in 1 plus R2 by R1. Right? And when we do that, AOL goes to very high. We find voltage at the inverting node is equal to V in. Correct? So that's what we say the voltage here is simply equal to that. Okay? Agreed? So we've gone through the derivation here. What is this? Look at that now. What is this circuit? Isn't this the same as this part that you see here? R1, R2, and the voltage is here. Remove the R and C. Isn't it the same? There's nothing but a Schmidt trigger. Correct? Okay, so now we are applying, you're right, there's a positive feedback here. What will be V0 now? V0 would be, if you say it's a Schmidt trigger, it's a comparator, what would be the output? Plus minus? Positive, close to positive VCC or negative VCC? Let's do the analysis. Tell me where the flaw is. So let me start here. The current here. How do I write the current? 0 minus the voltage now at the positive terminal, V plus by R1. Okay. Op-amp's input impedance is still very high. It's not drawing any current. So the next thing I write this current. This current should also be equal to I1. So I2 equal to I1, V plus minus V0 by R2. Right? Same. The only thing I've made is the input, no current is going into the op-amp, which is fine. If I rearrange this, I get V0 equal to V plus 1 plus R2 by R1. Next, what do I write? This equation is still valid. Op-amp, the output voltage of the op-amp is open loop gain multiplied by V plus minus V in. So I extract V plus from here. Okay, I extract from here and substitute here. I get this one. Gain of the op amp is, and this is this one here. Gain of the op amp is very high. I get V in 1 plus R2 by R1. All right. Where is the? Do you see any flaw in this? So this model is no longer correct. Why is it no longer correct? Suppose I go ahead and simulate this. I take microcap and simulate. What do you think it will give? What will it give? This is saying V0 equal to V in 1 plus R2 by R1. All right, let's do microcap. Let's see that. I have the circuit with me. Here, can you see the two circuits? In one case, I've applied 0.1, which goes to the positive terminal. And this is the circuit with a normal negative feedback. And in this case, I've applied it to the negative terminal. The circuit is with the positive feedback. So one with positive feedback, the other one is with negative feedback, right? These two circuits are there. Okay. And what do I expect? 0.1 as a non-inverting amplifier, 0.1 multiplied by 12. The gain is 11 by 1, so 12. So I expect 1.2. So let me run analysis, dynamic DC. What does it give me? (1.2) and 1.2. 1.2 and 1.2. So it's giving us what we expect. That this is also working as a non-inverting amplifier. This one is also working as a non-inverting amplifier. Both are working. Both are giving us the same result. What should I do here to change? You want me to run the transient analysis? Not the dynamic DC. So let me run a transient analysis. Transient. And I'm looking at the two nodes, output nodes, V9 and V14. So right now I'm taking ideal op amp. Both are 1.2. Both are 1.2. Ideal op amp. These both are ideal op amps. Whether I run steady state or whether I run transient, the output is 1.2, and we know this is not right. We know that this is a Schmidt trigger. This is a Schmidt trigger. It can't be. It can be only in the two states, plus 12 or minus 12, right? So how come? Where is the mistake? Why is this making a mistake? So it's not that there is a problem with my analysis. The simulation is exactly telling what my analysis is also doing, right? Your point is right that I may have some disturbance, some noise in my circuit. What does that noise do to my circuit? If let's say this is like assuming all this, that when I do analysis, dynamic DC, it does steady state analysis. Everything is constant, steady state analysis, right? And even when I do transient analysis, it's an ideal op amp, and ideal op amp responds, it has got no frequency response, so it responds instantaneously. So it reaches steady state immediately. It just goes into steady state, an ideal op amp. So let me take this ideal op amp, let me introduce transients. A little bit transient in this one and this one. So that, so for feedback to operate, you realize that there has to be some delay, and, the signal from output is fed back to the input, then it affects the input side here, and then it propagates to the op amp, and then it changes. There has to be a little bit of delay for the, for proper feedback to properly operate. So I want to introduce a little bit delay here. Okay, so how do I introduce? So suppose, for example, one way is, that delay can be introduced through capacitors. So suppose I take a capacitor here and I add to the output. Okay, I add to the output a capacitor, and let me just arbitrarily put some large capacitor, 100 microfarad. 100 microfarad capacitor I put here, and I put here ground. Okay. So now what will happen is, even though my op amp is ideal, because of the capacitor, things are not going to go to steady state immediately. It will take a little bit of time to reach steady state, right? So same thing, let me do it in both cases. All right, fine. Let me run the transient analysis. Transient with some time, let's look at it. See the result now? The V9 that you see here, that's the output of the non-inverting amplifier. And this one, the blue one, is the output where I have positive feedback. So see what has happened. This one, let's look at, let me put the cursor here. So let's look at the red one here. Because the capacitor was initially discharged, it was 0. So the voltage builds up across the capacitor. You know, it builds up and eventually it reaches where? 1.197, 1.2, which we expect. The gain is 12. So 0.1 multiplied by 12 gives us 1.2. So my non-inverting amplifier is behaving as it should. It takes a little bit of time now to reach the steady state. Look at the Schmidt trigger part, which was earlier giving me 1.2. Where does it start? Look at V14. V14, and this is the output here, okay? V14 here. So what does it give me? Can you see what is happening to the blue one? Starts from millivolt or starts from 0, builds up, keeps building up. Note that 1.983 keeps building up. And then keeps on building. Minus 324. Keeps on building here, right? So it eventually goes to, it's an ideal op amp. There's no limit on how high the voltage can go. And what is the positive feedback doing? It just keeps on building it up. There's no limit to the output voltage here. It just keeps on going, and eventually, of course, it's going to giga and all that, right? So the steady state analysis is not giving us the right answer. Real life, you know, when you go and make the circuit in the lab, you will switch on the power supply. You are and your op amp has transients in it. It has a frequency response. It has a delay in it. And so what you end up is getting into this kind of a phenomenon. You don't go into steady state directly. You will go starting from some initially uncharged value, let's say 0, and then you go, right? And then as you go, then the differences crop up between the two circuits. So simply doing steady state analysis is giving you the wrong answer. How you arrive at steady state is important. And once you do that, then you see that the positive feedback is giving you, the output is being driven towards very high value here. And the negative feedback, of course, goes to the required state here. So, which is also, you can see from here, right? Which is also from here, that if I have a negative feedback system, let's say initially this is 0, right? And I apply 0 to 0.1, suddenly I apply 0 to 0.1. What happens? I develop a voltage here between these two nodes, 0.1. And then after a delay, as it goes through the op amp, what will it try to do? Force it up. This voltage will try to increase. As this voltage tries to increase, what will happen to this node? This node, this is nothing but like a voltage divider. So this node goes up. And what does this tend to do? It tends to decrease the voltage between them. And so up to what value can it rise? It will rise to a value such that this one becomes exactly equal to this or very close to this, so that the op amp cannot raise it any further. So there's a negative feedback which is working, which will drive it to the required value. Look at in this one, if this is 0, and when you apply 0.1, this will tend to rise, or this will tend to fall now because it's applied to the negative terminal. It will go to the negative direction. This will also go in the negative direction. And what happens to the voltage drop between here? Increases, because this is positive. So the voltage drop between here increases. So this will become even more negative. And then this will, the positive feedback will keep on driving it to larger and larger negative values. Eventually, the supplies will saturate it to minus 12. So when you look at steady state, then we get into these errors here, right? We get into this error. Both of them seem to be predicting the right, but steady state is not the right way to analyze these particular circuits here. When you look at it, how it comes to the steady state, then you see the differences between them. Okay.